Investigation 9, tessellations. Tessellations sometimes called tiling, and that's because it's a repeated pattern of plane figures that completely covers a plane with no gaps or overlaps. So they're asking us to take this equilateral triangle, slide it to the right so that they share an edge. Wait, slide it. Oh, rotate it 180 degrees and then slide it to the right so they share an edge. So that's like when you rotate it 180 degrees, this pointy side will now be down. So basically they're saying draw it like that. And then rotate the second triangle 180 degrees and then put it next to it. So this is saying, does the triangle tessellate? So can we continue to do this and there won't be any gaps or overlaps? Yeah. Can we do that? Yes. Okay. Repeat the tessellation for a few rows to create a parallelogram. So they're saying, well, let's do another one, like maybe down here, continue going across. They said they want us to make a parallelogram. So that means we need one more here. Wait. Yeah, that's like a trapezoid. So how do we make it? I feel like, oh, like that, sorry, keep going. No, that's not a parallelogram because that means I have to do, I bet you have it. Yes, just like that. So, I still can't get that end, like I still can't get it to go.
Add one on this top row, upside down.
One more on the top, oh yeah, like that. Okay, there we go. Okay, parallelogram. Okay, how many triangles meet at each vertex? So here's a vertex.
6.
How many triangles? 6. Yeah. And what's the measure of each angle? So it's 60 degrees. So what are the total angle measures that meet at a vertex? 360 degrees. So we're going to do 6 times 60 degrees. A regular polygon will tessellate if it's interior angle. So it's one of the inside angles measure. So if the interior angle measure is a divisor of, what can you guess? 360 degrees. That way you can actually rotate it all the way around and you won't have any gaps. So to find the interior angles of a regular polygon, we take 180 times n minus 2, all divided by n, where n's a number of sides. So let's say n is 4. Let's figure out what these will be. So 180 times 4 minus 2, which is 2. So 360, and then divide that by 4. 90 degrees.
What's that black space?
That's for the label. That's to help you remember to put a label there. And then for n equals 5, we have 180. Whoops, I put an n in there, but that should be a 5. Times 3 divided by 5. What is that? 108, okay. And then 180 times 4 divided by 6. 120, and 180 times 5 divided by 7. It's like a decimal number. 128 and 57/100ths. Okay, so now what we want to do is we want to divide 360 by each of these degrees and see if it's a divisor. So 360 divided by 90
4.
degrees is 4. 360 divided by 108. Does that go in? 108. Oh, it's 3 1/3. 360 divided by 120. That's just 3. And 360 divided by 0.57. It's like 2.8. So which one of these will tessellate? Oh, the 90 and the 120. So how many sides? So a four-sided figure is a regular four-sided figure. Square. And a six-sided figure, hexagon. Okay. Those two figures will tessellate. So I think we're supposed to draw them. On number 6, we're supposed to draw a tessellation. Make a sketch of the tessellating regular polygons you found in problem 2. So with a square, we can make it a square. Basically, they can just fit side by side, top to bottom. So here's a tessellation of a square. Now with the hexagon, I think it's a little bit harder to draw a regular hexagon, but we shall try. Oh boy, that's really bad.
Hexagons in the first place.
I know. But yeah, mine doesn't look very good either, so. You can kind of get the idea of what it will look like. They should all kind of go together like that.
I wish goldfish were able to tessellate like.
Oh, that'd be
so many
awesome.
times.
That would be awesome.
You know, it's sad.
Are there regular polygons with more than 8 sides that can tessellate?
What about 10 of them?
10. So,
Well, 360.
wait, so we did
So it would be 8 times 180
divided by 10. So 8 times 180 is
288. Yeah.
wait. I got 144.
Well, I divided it by 360 times 8.
Oh, is it 360? No, it's 180. Remember we do 180
Oh yeah.
times 8 divided by 10. I got 144. Does 144 go evenly into 360? So wait, 360 divided by 144 is 2.5. So it's not
About
a
12.
divisor. 12. So 180 times 10 divided by 12 is 150. So no, 360 divided by 150 is 2.4.
No,
Doesn't
because the
work.
polygons with more than 8 sides have exterior.
Interior.
Interior.
Yeah. It's actually no, because they have interior angles measures than 120, so greater. Yeah. The only other divisor of 360 is 180. Oh, and there's not a polygon that can have 100 interior angles that measure 180. Because then it would just be a straight line. Yeah. Oh. Okay, possible regular tessellations. So far we've come up with equilateral triangles, a regular square, and a regular hexagon. Okay. Now we have what's called a semi-regular tessellation. So it's a repeating pattern formed by 2 or more regular polygons in which the same number of each polygon occurs in the same order at every vertex and completely covers a plane with no gaps or overlaps. I imagine, like, have you guys ever seen that old linoleum that goes on bathroom floors sometimes that has hexagons and squares in it? That's what I think
I
of.
stare at it. and,
Is
like,
that,
look
yeah,
pictures.
those are tessellations, if it has the squares and the hexagons. So it's just saying if you have two or more regular polygons. Okay, so, number 9, okay, so number 9 is actually in the book, and it has a tessellation of those squares and octagons. So a semi-regular tessellation is made of congruent regular octagons and congruent squares. So how many polygons meet at each vertex? 3, yeah.
No, would it be 4?
Wait, so here's a vertex. I see two octagons and 1 square at each vertex. So 3 polygons. The interior angle of a square is 90 degrees. And the interior of a regular hexagon, wait, that should say octagon, don't you think? Let's cross that out and say octagon. So that would be 180 times 6 divided by 8, 135. So 2 octagons, so 2 times 135 plus the 90 degrees, that should give us 360. Yeah, 360 degrees. So they can tessellate together because their interior angles add to 360. Create a tessellation by translating the parallelogram. Okay, so we just have to draw one next to it.
I did it smaller.
I know, they really should have done it a lot smaller.
A lot?
It's one of those things that you just keep going on and on.
I know.
I'm just continuing. Okay, so anyway. Okay, so number 11. Will every parallelogram tessellate? What properties of parallelograms indicate that they will or will not tessellate? What do you think? Yeah.
So is it asking, do all parallelograms tessellate?
Yes.
I would say no.
Yeah, I think it's yes because like 2 of their sides always add up to 180.
Yeah, because two, like,
Yeah.
angles that are next to each other, so adjacent angles
Add to 180.
add to 180. So that's 180, and that, so together they would be 360. So yeah, it is a yes, because the vertex of a tessellation contains one of each of the parallelogram's angles. Oh yeah, because look. So here's the parallelogram. This is the top right. Here's the top left, the bottom left, and that would be the bottom right. So all the angles of the parallelogram will meet at one vertex. Oh, that's sweet. Since the parallelogram is a, yeah, it's a quadrilateral. So there's 4 sides. Quadrilateral. Its angles sum to 360 degrees. Number 12, will every quadrilateral tessellate?
Yes.
Yes. And that's because the sum of the angles of any quadrilateral is 360 degrees. So tessellations may feature different kinds of symmetry. So here's a few tessellations. Let's see. Which tessellation above is semi-regular. So if you remember, semi-regular means that they are
C.
made with 2 or more regular polygons that occurs at the same amount at each vertex.
C.
So it's C. So the tessellation consists of,
Triangles.
so they're talking about just the hexagons. They're congruent, regular hexagons. And congruent equilateral triangles. Good. And there are 2, so at each vertex, there are 2 hexagons and 2 triangles at each vertex. I don't really want to rotate about its center, but maybe we could
I'll come up with our own.
rotate around here. That doesn't look the same. That one doesn't really look the same. I don't think A has rotational symmetry. What about B? Does B?
Yeah.
So that means, and C does too, huh? So B has what degree rotational symmetry? How many degrees before you see the figure again?
180. No, 90.
90, yeah. And then C would be, and C has what degree rotational symmetry? 180. So which of these tessellations have lines of symmetry, and where are they? So we need to draw our lines of symmetry.
B has. No, it doesn't.
Does B? Does A? That kind of looks like to me that it does.
Oh, yeah.
And we're supposed to draw it in, so go ahead. Draw it.
Yeah.
And then B.
I don't think C does. Wait, yes, it does.
Oh, C.
Yes, two.
Yeah, C does. Oh, does it have 2? So if you go, yeah.
It does.
And vertical and one horizontal.
Okay, so A and C have lines of symmetry. Okay, so then there is a lesson practice. So they have a picture of a trapezium, and the question is, here's what it looks like. Okay, so if you do 180 times 4 minus 2 divided by 4 is 90 degrees. So is that, or is it not, a divisor of 360?
Yeah.
Yeah, so it is a divisor of 360, so the trapezium will or will not
Will.
tessellate. It will, okay. And let's just skip the rest. We'll be good.
Yay.
Yeah, we're good. That's it.